Hello, everyone, and welcome to our Twitch session today on what's new in image processing. My name is Shadi Ashnai. I'm the manager of image processing here at Wolfram Research. And this is the page that I'm presenting today with my colleague, Julia Alessandrini, trying to respond to questions and maybe at some point showing some examples. Image processing has been a part of the language since version 7. So it's a number of years, a number of releases that we have had image processing capabilities within the Wolfram language. The focus for us in the recent releases, definitely 11 and 12, has been to utilize the modern machine learning and neural nets capabilities that are as well built into the system, and make sure whenever we can create a function built into the system that can leverage from those capabilities to enable efficient and more accurate image computations, we do that. And then in addition to that, we make sure the foundations are available so that if someone would like to build a machine learning or neural net-based application for image computations, that's also smooth, easy, and efficient. In addition to that, we have been looking into a large number of other additions into different areas of image processing. We haven't left classical image processing alone, so a lot of things such as key point detection and filtering and segmentation, and all of those have been seeing advancements as well. We have also been looking into application areas, such as a few that we have listed here: photography, microscopy, astronomy, and a few more, to make sure anytime we are tackling an application in those areas, there is no big missing piece within our set of capabilities. So basically, with that big introduction to what has been our focus for this release, I'll start talking about the examples that we have created for this marketing page. The first row of examples here is trying to show, as I said, put the focus on machine learning neural nets, built-in object detection, improved face detection, facial feature analysis, such as gender, age, and so forth, are two samples of built-in additions in Wolfram in version 12. In addition to that, Wolfram neural net repository that is hopefully being well known now contains the majority of networks work on images. So roughly 70-75% of the networks in the repository are image focused. So there is a large number and even growing number of networks that can be accessed through the Wolfram neural net repository. And this last example in a row is trying to show custom application development, in this case, classification of a data set using our neural net capabilities. So I'll jump into details once I go through all of these rows later. One thing that we added in version 12 is an image pyramid construct, which is basically a multi-scale representation of any image object. There are two types, Gaussian and Laplacian pyramids, and both types are supported. More types are going to be supported. This row is trying to show that, introduce that construct in version 12, and then show applications using image pyramids, such as multi-scale zooming, efficient zooming and panning, multi-scale feature detection, and the famous fun apple-orange multi-scale blending, which is being applied to physicians. Color as well has been a major focus for us in the past releases. Image and color cannot be separated. We started by introducing various color metrics and color distances. And then in version 12, a new construct for color neighborhoods has been added, which enables things such as color replacement with some variations or better color segmentations and so forth. In that row, we also feature improved color quantization with new methods and more optimized. Mathematica or Wolfram language is known for being symbolic, and being able to enter a formula and then any variable of that formula being able to be any object of any sort that is supported in the system is a very strong part of the language. In in previous versions, we have had arithmetic and statistics for some objects and modalities, such as audio objects and time series. Version 12 introduces the same capability for image objects. So basically, one can ask for plus of multiple images or mean of multiple images and so forth. And all of that, like as if you're putting a number or a list of numbers, is just going to work. We're going to dive into some application examples, showing color effects or tone mapping or contrast boosting and so forth. The last style of that row is showing some built-in image effects into the function image effect that we have. And that closes off that row of examples. Another very major and important focus for us in the past releases has been building bridges between different modalities within the Wolfram language. Version 11 introduced a function called image mesh, which was converting any binary image into a mesh region. And that allowed any geometric mesh operations on that modality, that representation of a binary image object. Which either was not efficiently doable in the image modality or not well defined. Version 12 continues on that path and introduces conversion between raster images to vector graphics, and also adds a region image function, which enables going from any mesh region or any other region into grayscale or binary images. And as I said, this enables a complete workflow for going from one modality to another, do the processing, and going back. In this particular example, for instance, we are doing some smoothing in the image domain of that blue object, which was a region originally. We're going to look at it in details later. The same operation is also supported in 3D, and that enables applications such as finding an implant or the disc missing from a 3D model or something like that, and many more application examples. The last row of this marketing page, or the image processing example page, is basically a small sample of many other additions and updates that we have made into the system. Ranging from key points, new types of key points, using them for video stabilization, getting a sorted representation of boundary around shapes and using them for things like Fourier descriptors. And this example in particular is trying to create a hand-drawn version of contours extracted from an image and so forth. There is a lot more that we didn't have room to show all in this marketing page. And so related functions are listed down here. Obviously, related guides would be the most complete place to go to in order to see what are the updates and what is the full set of capabilities in each domain. We have also added a bunch of related links as far as things we have done recently, and most importantly, linking to other marketing pages, such as the machine learning for image, which we really thought deserves a specific attention with this release, because we have put a lot of attention into this. And then there's going to be a separate Twitch session specifically for that. And then it's worth mentioning that we have created a specific marketing page as well for microscopy. And this is basically showing our efforts into stepping into different application areas that image processing and image analysis can be helpful. All right, let's continue this Twitch session by diving into some of the examples. Let me start with this very first example, showing our built-in object detection and recognition. So in version 12, we have a family of functions for object detection. One of them is image contents, which is basically giving you the full content that can be discovered from an image. Here are all the sub-images that can be that was recognized to be a specific concept or a specific object detected, with the corresponding bounding boxes and probabilities. In addition to that, we have decided it's also very useful to have shortcuts such as image bounding boxes that can give us directly the bounding boxes here, and then ability to basically highlight the bounding boxes on top of the image. The example itself doesn't show it, but we have more functions such as image positions and so forth that are additional, or image contains Q, which says, does this image contain an object of one sort or another. Let's move to the second example of this marketing page, which is our improved face detection and analysis. We have had fine faces in the builds for a few versions now. This basically is what the evaluation of fine faces in version 11.3 returns. And as you see, there are only two rectangles, two bounding boxes returned in 11.3. The improvement shows all four faces are detected. I'm here highlighting the old results in green, old results in red, new results in green, and that already shows some improvement. In addition, in version 12 is ability to start looking into facial features of an image, such as age, gender, emotion, and many more, including facial landmarks. Where are the eyes? Where is the outline of the face, and so forth. And this one can be used for various applications. All of those, a few examples in the marketing page for machine learning for images, if you want to look at that on your own. Okay, let me come back to this page and actually go through these other two examples that I had on the first row of this page. One of them is trying to basically show off the Wolfram neural net repository. And as I said, if I search, there is a lot already growing number of neural nets that are working on images. And out of more than 80 that we have, almost 90, I think, there are majority of them working on image objects. The types of applications that can be tackled using neural nets are very different. From image translation to segmentation to image identification, object recognition, colorizing, and so forth. There is just many networks that can tackle different applications or different problems. Here in this example, we are picking one sample, which is basically doing getting an image as an input, and then has so many semantic objects and is trained on these objects and can basically get that image as an input and return a label matrix, which in this case includes these set of objects from the labels. And here we are colorizing the result of that segmentation. As I said, this is just a sample. Feel free to browse through many other networks that are in the repository. In this particular example, we are showing a classification example using Fashion MNIST, which is a version very similar to MNIST on handwritten digits. This one is on 10 classes of different apparel types. And we are basically getting LaNet as the network to train and getting that training data, test data from Fashion MNIST, and train LaNet, which is also available through the net repository, and then train it on Fashion MNIST. And as you can see, the neural net capabilities easily allow us to get the accuracy measure or visualize the confusion matrix coming out of that network. Okay, so that concludes the part on machine learning. Let's start looking into some of the image pyramid capabilities and examples. So as I said, pyramids are new constructs or objects in the Wolfram language. Here I'm constructing a Gaussian pyramid, which is basically downsampled, stores downsampled versions of the original image itself. So this shows the list of images that are stored in image pyramid, downsampled by the factor of 2. The downsampling factor can be specified as well. And then this other call creates a Laplacian pyramid. And then these are the images stored in the pyramid itself. From either one of the pyramids, we can reconstruct the image itself by calling inverse image pyramid. Now, that on its own is not that exciting. Obviously, when it comes to application example, is where we get more exciting effects. Let me jump to this example of multi-scale image blending, which we start by simply splitting and assembling two halves, left part and right part of the two images to get a not so smooth blending. And then by doing the same operation on every level of the two pyramids of the two images, we basically blend all the features at all the low scale and high scale features of the two images. So the blending can be done a lot smoother. And that's the result. All right. The next row, as I said, is the color neighborhood topic. The construct in the system introduced in version 12 is colors near. Colors, as I said, colors, perceptual color distances have been introduced into the system already in previous versions. Colors near is trying to represent a neighborhood of an image with respect to a specific color distance. And then the value that is put in the second argument is basically the distance, how big or small I want this neighborhood to be. And so here we're representing or plotting three neighborhoods, three color neighborhoods around almost reddish, green, and bluish centers with the 0.1 radius in the default I think CIE 2000 or one of those. We have the defaults documented in the builds. And then in a 3D space. And then this one is showing the same chromaticity plot for the color neighborhoods of the same three colors with a slightly larger distance so that they are bigger and more obvious, using a CIE 76, which basically is the Euclidean colors, Euclidean distance in the LAB color space. So in that case, all of the neighborhoods are perfect spheres. Continuation of that example shows a green screen example, which is basically using that colors near to say, get me all the colors that are within that color neighborhood, and then set that binary result or a grayscale result as the alpha channel of the image so that it's masked. One of the fun things that has been added into this version, come out of full screen. Is image recolor. Image recolor is basically a function that can take a color or a color neighborhood and say, replace this or that color of the original image and all the colors that are within the vicinity or neighborhood of that color with another color. So in this case, we are replacing all the red, darker pink colors with this green and all the pinks with that blue, everything else with white. And the marketing page continues with some various examples, but here, demoing this live, I basically created this nice manipulate that I can say where my dark pink want to get mapped to and where should the light pink get mapped to. Okay, let's take another sample of this row. For instance, let's look at the color quantization example. As I said, we have had color quantize in the system for a while. We had one method implemented. We now have more methods implemented, improved implementation, both for quality and speed in version 12. And this basically shows the quantization for 3 sample methods for 3 sample colors, target colors, and so forth. Okay. I would also like to show a few of these image arithmetic and statistics operations. As I said earlier, it's very natural for our language, for our system, to be able to simply say 2 times the object, no matter that object is a number, is a time series, is an audio, or now newly introduced in version 12, is an image. So here is the same image from the page, and I'm doing the same operation as it is here. And as you see, we can just simply put a formula like that, without needing to combine so many image operations, image this, image that, and do whatever operation as we want, such as changing the brightness, changing the gamma, or increasing or decreasing the effect of highlighted edges on top of the image. More examples on that row. As I said, the second one basically highlights prototyping different ways of tone mapping the image. This image has a lot of information in the dark area that is not visible, a lot of information in the supposedly brighter areas of the image, and none of them are that much signified. So we are starting by prototyping something very simple, 2 to the range of 2 to the power of anything times the image, to see what's the effect of such an operation on the image. Then we make it a bit more complicated and apply this function to the image to rescale the brightness. Or we could use the log function on the image with some small bias, and then get some other tone mapping algorithm implemented. So as you see, all of these are very simple, very immediate and direct. Image is simply one argument of the operation, and the operation is applied to every pixel of that image. And we can see what's the result to either prototype or see the effect of the prototyping. And the third example in that row is basically roughly the same thing. We're also making use of more statistical operations, such as mean of all images and so forth, which again is operating on corresponding pixels of images passed to the functions. And this last example is trying to show a few of the additional image effects that have been introduced in version 12. All right. Let's start looking into the next row of examples, which, as I said, is the bridging row of these examples. First example is trying to show a function called image graphics. To begin with, we are starting with that image of the rows. We are doing some smoothing so that some of the noise is reduced to get a better vector graphics out of the image. We can get dominant colors of the image to control things a bit more, but image graphics without the colors as well could work. And this is a vector graphics representation of that image. If I click, 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 you can see all of these are polygons colored with the corresponding color from that region of the image. And I can switch to different regions, different colors. If necessary, move them around, scale them, and so forth. So this is a real vector graphics representation of the image. Let's look at the next example, which is showing the bridging between regions and images. Here we are simply creating a 2D region, starting from a notch curve, and then rotating in and repeating the rotations to get a 2D shape of that region. Region image is the function that can basically rasterize this region into the range of whatever in the X and Y domain that the region has. And this is basically an image representation of that same region. The same function that we used in the previous example for smoothing, curvature flow filter, is a smoothing filter that is very well defined and efficient in the image domain. So we basically run that on the image to smooth out the corners of that region, and then convert that, and then this is the result that we get back. Using the other conversion function, image mesh, that was previously introduced in version 11, we can convert that image back into a region. And then here I'm showing, I'm using region difference to show the difference between the smoothed region and the original region, which the operation basically happened in the image domain. Going back to our page, I'll just show the 3D version of the same operation, region image. So here we are starting with a region representation imported from an STL file of a 3D vase. Using that region image function, we convert that to a 3D raster image. then we can use any of our image processing functions, such as closing, filling transform to fill the holes, and then blurring if necessary. And then this one is basically showing the effect of dilating the vase and whatsoever. And then again, image mesh could be used to take the object back into the original modality. The last example of that row is basically using the same functions, image mesh and region image. Here we have the CT scan of the spine, and we start from the 3D image. We binarize it to get a good segment of the bones, and then we basically find the gap between the two bones using image processing operations, and then convert that to a mesh representation, which could potentially then be 3D printed and so forth. With that, I'm going to go to the last row of example, which, as I said, is just a sample of many other additions in the system. More types of key points have been added in version 12. And this example, for instance, is a very good example that shows, for instance, ORP that is a much faster key point introduced in version 12 can be used for, let me play this video on the top, can be used for tracking the points from one image to the next in the sequence of images taken from a video. And then in this particular example, we are masking. We're using this mask which has white only at the bottom, which is highlighted here on the image, and use the corresponding points from the mask region only to perform image transformation on the sequence of images. And then this is the result of video stabilization. And then, okay, let's quickly switch to this example. As I said earlier, the boundary representation of a shape is another addition in sequence, is another addition to this, to a function image measurements and component measurements in version 12. We are using this small addition to create big applications such as gear counting in this example. Using a simple binarize and filling transform, we can get a good binary representation of an image. And then image measurement perimeter positions returns a sorted list of positions on the boundary, which can then be highlighted on top of the image. Here we are defining a few utility functions to find the defects of the convexity defect of the shape. And in this particular case, we see that there are 28 feet. Another utility to basically draw graphics of the original contour, the convex hull, and the points representing the peaks that were counted. And then basically this can be used, all of these are being used to summarize the result of this teeth counting. This is basically the distance between the original contour and the convex hull, and then the peak detection on that gives us the number and then the position of all of these peaks. The example in the page itself continues with a more with a bigger image containing many gears. And then basically what we're doing is doing the same, exactly the same operation to find the contours and then count the teeth and classify them with the number of teeth. And here are some results that are shown. The same contour property or pixel perimeter position property can be used here to construct the Fourier descriptor on the contour, which can be used as a smoothing mechanism for a shape of an image. Here we are showing different smoothing for the cat picture. And then as we scroll down, we have a more sophisticated image under that mask and edge detect. This is what we have. And then we can combine the different scales of different Fourier descriptors in order to get such a hand-drawn version of the image. I think that concludes the Twitch session for today. If there are any questions, I'm happy to respond.